Okay, so now we've seen that classically speaking, if an electron were to just orbit in a circular orbit around the nucleus, okay, then classically speaking we would estimate that the electron would radiate all of its orbital motion, all of its orbital energy in about 10 to the minus 10 seconds, and would spiral into the nucleus, and the basically the hydrogen atom would collapse. Okay, so we know that doesn't happen. Okay, and we know the reason why that happens is that does not happen is because quantum mechanics basically dictates that the electron can be thought of as being part of a wave. The wave function, if you square the wave function, that gives you the probability density of finding an electron at a particular point in space around the nucleus. And because it has wave-like properties, it can have basically stationary states, eigenstates, or standing wave solutions, for which the probability density doesn't depend on time, and therefore it doesn't radiate. Okay, so in particular, let's suppose that time equals 0. Okay, at some particular time, which we'll just set to be the 0 of time, we have a system, for example, a hydrogen atom that's in some eigenstate of the system, the nth eigenstate of the system. Okay, so that means that we can write the wave function, which is a function of position and time. At time equals 0, we can write it as just the nth eigenstate, psi sub n of r. Okay, and obviously the total mechanical energy, of the electron, the particle, is E sub n. Okay. Now at some later time, the system has evolved. Okay, and so the eigenstate is evolving in time. If we think of a standing wave solution, then the amplitude is oscillating in time, and so this is the time-dependent part of the wave function multiplying the spatial part of the wave function, which is an eigenfunction in this case, an eigenstate, and so the time dependence is dependent on the energy E sub n. It evolves according to the energy E sub n of the state. Okay, and the probability density, as we've seen many times now, the probability per unit, this should be per unit. This should be per unit. This should not be. Let's see here. Hold on. Okay, so I changed this. This is the probability. The probability density is the probability per unit volume, or the probability per unit distance if it's a one-dimensional case. Here we're just subsuming the general three-dimensional case. So before I had written dp dt, probability per unit time, but this is now I have it correct. So anyway, the probability density is equal to the magnitude of the wave function squared, which is equal to the spatial part squared plus the temporal part squared times the temporal part squared. And because this complex exponent has unit magnitude, then this basically just goes to 1. Okay, and you get the probability density is equal to the eigenstate, the wave function squared, and since it's an eigenstate, it doesn't evolve in time. It's just a function of r position. Okay, and so we see that the probability density and the corresponding charge density, if the particle is a charge, is an electron or some other charge, is independent of time. Okay, and since the charge density is independent of time, then there is no radiation because there's nothing accelerating in this picture. Okay, and just as an aside, this actually, if you think back to your classical electrodynamics, electricity and magnetism class, and you think about a current loop, so just a current going around in a circle, certainly the charges are actually accelerating in the sense that they're going around in a circle, but in fact that steady current loop, if it's going around at a constant speed, does not radiate either.